He's like, sorry, just cancel that.
Yeah.
He said he was gonna drop our load. I was thinking that I would get like
Stop working on it. My buddy called me and said, hey, need some help. Gets better. Let me know.
Yeah.
They are, I'm finished. Get over there. He bought a dump truck. Hey, you know what? He bought a dump truck like last week and he's like changing the brakes on it. Dude, and these brake rooms are like that big. Like we had to take a sledgehammer and put them back on. Use a jack just to raise the rotors up. I don't know why.
Okay, gang.
Bought a dump truck.
Here's corrected homework.
That's crazy. So I ended up drinking a couple
And
beers
here
and
is the
working on
quiz. Actually, might as well not have taken the quiz, right? Because everybody did very well, I have to say. The average was about 8.5 out of 10. So, in some sense, you know, if you got like 8, or you got 10, or you got 7, you didn't gain much or lose much. But anyway, here we are. These are the proper color. Oh, we'll start. All right.
Last time you saw that.
I have a homework assignment. And the homework assignment, hey, listen up. I assigned for today G20, but I'm not collecting G20 because it's on mutual inductance and I didn't really lecture on it. I'm going to talk about that now. So G20, but I made up another one, G21, on energy. So I'm going to talk about self-inductance, mutual inductance, and energy in inductor, and energy density in space wherever you have a magnetic field. All right, that's the agenda for today's lecture. And then associated with those topics are these two problems. And I want to say a few words about it when I get to it. Here is that G21, and if you read my notes, you'll find, actually, the solution to this. I mean, in other words, this is just forcing you to take a look at page 262, or what the page number is, and convince yourself, yep, that's the derivation. And so, again, it's an easy problem, but it's forcing you to kind of look at things. And at the last lecture, what I did is I handed out a set of notes, which were actually homework problems that I decided not to give, on mutual inductance. And here I have another set of notes. And you'll see the title of one is An Example of Mutual Inductance. An example of mutual inductance. So I want you to read this too. I mean, I don't have that as a reading assignment, but it's another example of mutual inductance. And when I get to it, I'll talk more about it.
When is G21 due?
20 and 21 are due Monday, according to that. Okay, so unless you have late homework, I am not collecting any homework today, but if you have late homework, you can put it in here. Okay, let me draw a picture first. Here's a loop of current. Right? So let's say the current is flowing that way around. I'm picturing this. Here's the loop of current, I, and it's the free sort. Oh, it's a free sort. That means you can double this, triple it, reverse its direction. It's under your control, okay? And then we use our right-hand rule. We put the, maybe I should make the current go the other way, huh? Make it easier. I put my thumb in the direction of the current, and the magnetic field and now the H field, those two fields related by that mu business, is coming out of the top. Let me do the color for that. Coming out of the top, going into the bottom. Of course, it's all over like this. I won't draw a lot of them. But this could be considered to be B, and if you want to draw another one a different color, H, and those two are related by B. B is equal to mu H. But the H is nifty because it's this thing that you're controlling. In other words, I'll think of, well, let's not talk about B at this point. If I double this current, I'm going to double H. And even though this might be a big, fat, thick iron wire where you have not only this stuff flowing, but you have that other strange magnetic current. It's current, but I mean it's of the magnetic sort. Even though you have that damn stuff flowing, ain't got nothing to do with it. All right, so if you make the iron with a mu, which is 10 times mu 0, or you make the iron, which is 100,000 mu 0, in which case that current, that induced current of the magnetic sort is quite different. Doesn't matter one bit. If you set this free current to be 1 ampere, that's it. You have set H. And it doesn't give a damn about what the mu was and the B that came from it and everything else. It's only dependent on you. All right? That's the nice thing about it. Now, this is the way I'm looking at it here. I'm picturing this as maybe in air. Well, actually, it could be in water or something because water has the same mu as air. Or it could be copper, or it could be some plastic or something. They're all with the same mu 0, all right? But I'm thinking of it as in air. And so you have a current that is causing an H field of some sort, and because this is a small number, the B that goes with it isn't particularly big. So what did we say we did? Oh, I don't think I'm going to wrap this guy around air. I am going to wrap it around iron. So I'll picture an iron pipe, right? And then I will, how did I make this go? Like this. Have that current I of the free sort wrapped around. And now I'm thinking of this is one turn, but you could wrap it many times, n times. So technically you should have n and n, I suppose. Just think of it as well. It's wrapped around. Let's see. I chose that. Yeah, okay, it's the right direction. And again, this is going to create a B field. But this B field and this H field are going to be pretty much in the iron. In other words, it's going to circulate around just like it's circulating around here. But it's not going to want to go out into the air so much as to stay inside and circulate around. Just like I said, if you had a battery and you attached a copper wire, it's most likely that the current that's going to flow is going to be in the copper wire and not flowing out in the air, because the air does not like to conduct electric current. But copper loves that, so that's where it's going to. Same thing here. Yeah, I suppose you could have some of this magnetic flux flowing out into the air, but it's a lousy conductor, so to speak, of magnetic flux. It loves to flow in iron, so it's all going to be pretty much 99.9%. It's going to be running around inside this tube of iron, all right? This hunk of iron. Got that? And so I can control the H. I mean, same as I can control the H by controlling this. And of course now, inside the iron, which is not mu 0 anymore, but maybe mu is equal to, let's say, 10,000 times mu 0, holy smokes, then the B field that goes with it is 10,000 times bigger than that would have been for the same amount of free current flowing around. Got it? Got it? And then the question is, well, what the hell good is that? Well, that's when I brought in the idea of wrapping a second coil around. And this is the primary and this is the secondary of an iron core transformer. And then we find that there's a voltage induced here as a function of time. It has to be as a function of time. This is AC. AC transformers don't transform DC, you know that. But let's, in other words, we're not in a time varying situation yet, but let's say we were. This was time varying. Then you would find that this would be equal to the rate of change of the amount of flux that's going through here. I'll write it like this, dt. But that flux is the area, the B dot ds, that's the flux. So it's the d of that stuff, dt. So this, if you, for example, have a very big B, you have a lot of flux, and you have a lot of flux changing with respect to time, 60 hertz or whatever it is, then you have a pretty good voltage here. On the other hand, if you just wrapped that coil here, yeah, you'd probably get a voltage across here, but it'd be far weaker because this B field is not very strong. This is a small number, so this is a small number, and then you rate of change it, and yeah, you get a voltage, but it's not. Now this is the air core transformer, and I talked about that. This is a linear transformer. The problem with this one is, iron ain't linear, and I gotta talk about that. That's my next topic. But if you don't drive it too hard, you might consider it to be sort of linear, and that's what we're gonna do in this course. We're gonna assume that it's linear iron, which isn't that realistic, but that's my next topic. Okay, so let's say I do an experiment. Let's say I start out with this current being 0, and this iron has never seen a B field in its life. It's a virgin iron, they call it. It's never been biased by any B field. And now what I want to do is I want to, beloved of all engineers, I want to plot something. Let's say I plot the B field in the iron versus the H field in the iron. Now the H field is proportional to Ni. In other words, remember I told you, if you double this, you double that. If you triple this, you triple that, right? So I don't care if you're talking about plotting it versus H or plotting it versus this. And I really should write it as I free. I did over here. Yeah, okay, I free. That's the thing that, so in other words, running up and down this axis is you. You're free to do that. And then you're asking Mother Nature, how much B are you putting in that iron anyway? So you start out with virgin iron, no B, no current. Then you start doing the thing, your thing. And your thing is on this axis, so you start increasing the current. That means you're increasing this H field, this amperes per meter. Okay, starts increasing, starts increasing, starts increasing. I know it's pretty linear actually. In other words, if I double the H or double the current, I double the B and all that stuff. But you find that in iron, what happens is it begins to do something like this. And then if you're at this point, you've got that much current, and then you double it, you really haven't helped yourself. You haven't driven more B field through there, right? It's what they call, it's saturating the iron. It just can't handle any more B field. And so that's nonlinear for sure, because in this region, think of it, if you take the slope at, let's say, that value of the current, it's equal to the B, this thing, over H. Oh, B divided by H. Oh, that's, the slope is mu 0. That's what's nice about that curve. The slope is the mu, all right? So I'll just write it. Slope equals mu. Well, if you drive the thing pretty hard, eventually you get over here, and over there, and over there, and all those slopes are different. I mean, here the slope is the same, but after a while, all the slopes are different. And then you begin to wonder, what the hell is the mu of that iron anyway? See, because it's not a constant. No, it's not. That's what makes iron so difficult. That's what makes nonlinear things so difficult. But, so, anyway, looking ahead, it's even worse than that. Because let's say you bring up the current to 3 amperes, and you saturate it like this. Now you say, okay, now I'm going to slowly bring the current down again. Okay? And I'll slowly bring it down, and I should, do this. But it doesn't. What it does is, okay, it starts, and then it doesn't follow the same damn curve. It does something like that, and then you say, well, I have got no current here. There's no current here, and yet there's a B field fluxing around. I mean, that's what this is saying. You have permanently magnetized the iron. That's what's happened. There's B field in there in spite of the fact that you have no free current forcing things. So then you say, well, if I can reverse the current, okay, let's reverse the current. So what happens is this curve keeps going down, and you drive it more and more in the opposite direction, and it saturates again. And then what happens is you say, okay, I'm going to reverse that, and then it comes, and it doesn't follow the same damn curve, and it doesn't even follow that curve, comes up and it does saturate like this. And then you try it again, and you get this sort of a curve. And now when you try and talk in terms of mu, I mean, mu is the slope. So over here, the mu is okay. I mean, the slope pretty much is the same, like that. But what is, I mean, let's say I have this whole curve now. At this, is that the mu, or is this the mu, or what is the mu of the damn thing? It's not only a nonlinear, but it's multi-valued. You see, really complicated. This sort of action of the iron is called hysteresis. It remembers. That's from the Greek, meaning its past had some, it remembers what it saw in the past. And so this curve here, which I've drawn it like this, that's called the initial magnetization curve. That's the starting out from the virgin iron and then forcing it into saturation. That's called the initial. But then after the initial and you back off, it doesn't follow that curve. It follows some other curve, and then you try that again and again, and you get this hysteresis curve, right? Now, this, I won't start that up. If you have iron that has, it looks something like this. That's, in other words, what I'm saying is the hysteresis curve is real skinny. And from here to here, that's pretty linear. In other words, there is a nice slope you could call mu. That's the kind of iron we're going to have. All right, this is soft iron. This is easy to magnetize kind of iron. This kind of iron is hard iron. Actually, it might have dual personality. Up to this point, it's soft, and beyond that point, it's called hard iron. It's hard to magnetize. So this one is an approximation to linear kind of stuff, except linear is just all, for every H, the B is proportional. But in iron, it does saturate. Even the soft iron does. So, but what we're going to do is either we're going to have soft iron, and we're going to assume that we're limiting ourselves to currents or H fields, which are in this range, so that we are linear, and we can define a mu as being the slope of that hysteresis curve. All right. There's all kinds of theories. The area underneath, like here, this area, has something to do with the amount of energy lost in the iron. You know, these guys are bumping into one another when they twist to and fro, and the iron heats up. So that's heat loss. And so this kind of a hysteresis curve has lots of heat loss, whereas this one wouldn't. This would be less, you wouldn't lose as much inside the iron, right? That sort of we don't have to go any further into that. But anyway, so what I'm doing here is just talking about, in general, the properties of, and the strange properties of iron. Right now, we didn't see this at all in dielectrics. But dielectrics, you can find dielectrics that do the same sort of thing. They have a nonlinear, they have hysteresis and stuff like that. This one allows you to, and I don't know, they call, if it's an electric thing, they would call it an electret, where you don't have any charge on the thing, but you still have an electric field running around in the dielectric. This one is very common. This is the way you would produce a magnet. This would be a lousy permanent magnet, obviously. Very little amount of B field if you have no current. This one would be a very good one for a permanent magnet, because no current, but you got yourself a pretty damn good B field, huh? So this would make a good permanent magnet. That would make a lousy permanent magnet. This point is called the retentivity, and this point is called the coercivity. And the fatter the thing is, the better a permanent magnet it is. Okay, all kinds of stuff like that. Well, we're not interested in the details of the iron, I want to get into the next step in my argument. That is mutual inductance, self-mutual inductance. And just like in the case of the electric world, I talked about capacitance as being, you think of a capacitor as maybe causing a reactance which is the negative of an inductor or something like that, a circuit kind of idea, huh? Here, I'm thinking more of an inductor or a capacitor as an energy storage device. You put energy in, 3 years later, you can get the energy out, right? In the case of the electric world, I called it, I think, WE, like it was 1/2 CV squared, where the voltage was across the capacitor, and that's the capacitance of it, which is the charge per unit voltage, and that's the number of joules energy stored. We're going to eventually come up with energy magnetic, and we'll have to figure out what that guy is. We had 2 ways to get this energy. This one was having the capacitance and the voltage, you got the energy stored, bam, like that. But then the other way was to get the little WE, remember, the energy density inside the region where the plates were, and then integrate that energy density, and you should get this same number. Remember that? Two ways to get this number. One from the field viewpoint, this one from the circuit viewpoint. We're going to have the same thing here. That's where we're headed. Okay. Well, in order to discuss one method, I'm going to have to talk about inductance. And we're going to call it L. And when I say inductance, I'm going to divide into 2 different kinds. There's going to be self-inductance and mutual inductance. And I'm talking about self-inductance. Self-inductance. And what that means is I have only one circuit. And I'm going to put current running around, some sort of current. And that current is going to cause an H field and a B field. I mean, call about that free. H field and a B field, they're related by B is equal to mu H. So someplace in my, if this was on a quiz, I'd have to write mu is equal to mu 0 everywhere, or something like that, all right? So that you know, oh, if I knew what H, I know what B is, it's related by mu 0, not 10,000 times mu 0. On the other hand, if mu was mu 10,000 mu 0, I'd have to tell you that. But anyway, there we are, current flowing, and it causes, well, thumb in a direction, is coming out here. So again, let me use color. The B field, it's coming out here, fluxing around like so. So let's say that's the B field. And there's an H field there too. Same thing, I mean, like that. So then you can ask the question, how much, what is this measured in? Oh, I'm thinking of it as flux. This is measured in Webers per meter squared. Remember? That's also called Tesla. But I'm thinking of, this is nice because it reminds me, oh, that's a flux density. So how much of that flux density is flowing here and here and here over this area surrounded by C? I'll call it S sub C or something like that. This bubble surface right here. So I guess you would say the amount of flux of the magnetic sort is equal to the integral all over this S surrounded by C of B dot ds. Like that. And I'll just picture it here. Here's a little square on the little bubble surface, and that has a normal and all that stuff. This is the ds. Got it? Just like that. We've done this before. Now I want to comment here. This is truly like a bubble surface. I mean, if you think of the copper wire around which the current is flowing as a little kid's toy, and you dip it into soap water, and then you lift it up, what do you see? You see a membrane across there, and it's kind of shiny, and that's and then if you blow into it, it bulges out that way. If you blow it the other way, it bulges out that way. If you blow too hard, it actually and it bubbles off, right? Well, I don't want to do that. I want to keep this surface attached to the little kid's toy, all right? But what I'm trying to say is this surface, S sub C, surrounded by C. C is unique, but S sub C is any one you want to make it so long it is sewn to the C, okay? Whether you blow into it or what. And I will talk a little bit about, when I talk about mutual induction, I'll talk a little bit about that more. In other words, if you want to do this integral, sometimes this one might be harder to do, like, for example, you might want it to be, if you're trying to find it, instead of having this as a surface, you might want to make it actually in the spherical system a dome sort of thing. And that's okay. See, that's better because it's easier to do the mathematics of this to get the flux going through it. Rather than through this flat surface, you would do it through a little dome up there at the top. So this is not unique. This, of course, is set. And this is whatever you want to make it to make this integral easy. Okay, so then we get the amount of flux. What's it measured in? Webers, because this is Webers per meter squared. You've integrated over meters squared. You get yourself Webers. Huh? This is in the number of Webers that's flowing through this bubble surface, whatever you've chosen it to be, just so it's touched by the metal contour. See, and then we define the inductance is essentially the amount of flux that is caused divided by the current that causes it. This is the self-inductance. Okay, and now you know. Like the B, for example, the B is down here and let's say it's up here, and you've chosen the ds to be, it has two choices, either it's sticking this way or it's sticking in the opposite direction. So the sign of this guy could be plus or minus, right? So you could get a minus sign or a plus sign for this guy simply because of that dot product, 0 or 180 degrees, and so that's the cosine. Gives a minus sign or a plus sign. So people never do this, but to be very careful, you say, I don't care what the hell sign you chose here. I mean, if you chose it wrong, so to speak, where the ds is not in the same direction as the b, and you get a minus sign, to hell with it. Just make it positive. Same thing with the current. I don't care if the current is going this way or that way. It's just the size of the current, okay? And that's the way you would write it. Nobody writes it that way. But understand that this thing has to be a positive number, right? Can't be a negative number. So this is a positive number. Got it? Always. And what's it measured in? Henry's. Named after Joseph Henry, who was he was a professor at Rensselaer Polytechnic. And then he eventually was the guy who founded the Smithsonian Institution. Have you ever visited Washington and gone to the Smithsonian, which is many different museums, all anthropological and historical and animals, and the Hope Diamond is there and stuff like that. He's the guy who was the first director of the Smithsonian, sort of started it in Washington, D.C. So Henry's. He's also famous, when I get into the dynamics, he's famous for actually coming up with an idea which is exactly parallel to, and maybe even more subtle and difficult than Faraday's idea of mutual induction. So I'll talk a little bit about Henry when we get there. Again, what we always do is we say, okay, what I'll do is I will plot the current versus the flux, or the flux versus the current. So again, I have a relationship. So if I start with 0 current, 0 flux, increase the current, increase the flux, increase it again. And if you have a linear system, if it is truly linear, if it's iron, then you got yourself a problem. But if it's linear stuff, well, then you get something like this. And then the flux divided by the slope is independent of how hard you drive it. And you know that in your circuits that you studied, linear circuits, this is independent of how much current is flowing through the inductor, right? Yes, that's very necessary in order to make all those differential equations for the circuits that you studied, constant coefficient differential equations, because this is a constant independent of the independent variable, I, that you have. So we have something that looks like that. Now if you have a nonlinear one, then you have something like this, and then, well, now you have different slopes, and then you have different L's. So you can talk about those as being, well, let's see, at that current, the local slope. And that would be the d phi over di. And that would be called the incremental, like so. And that guy depends on, oh, how much current am I drawing through it? So you can either write it like that, or understanding that, oh, it's a function of the damn driving current. However, this is the incremental. Now you can see that if you have a linear inductor, then the incremental is equal to, so you can say that this thing is equal to that for that case, d phi and di for linear inductor. Okay, linear stuff. And that's what iron isn't, unless we have this kind of iron. And that's the kind of iron we're going to assume. So we're going to assume always linear. It's got air or iron in it. Okay, and that's the idea behind self-inductance. And I'm going to use these formulas. I'm going to use those formulas later on, because next what I want to do is say, well, if it's good for one circuit, how about for two circuits? So there we have two loops. And when I say loops, they can be circuits of any kind. So here is, again, the first one, and the current I1, C1, S1, if you want to call it like that, like this. And 1, because I am going to have another loop around here, and I'll call it C2 and S2, something like that. And now the question you're asking is, okay, I got this current. Again, there's a B field that comes out, like so. And it's going to have its own self-inductance. I mean, we just studied that, right? But then now, if you got that guy, you've got a B field that's kind of poking through this one, right here, and then coming around like so. Okay, now this. So then you ask the question, how much flux is going through the second loop due to current flowing in the first loop? Okay, so we're going to define a thing called the inductance of the first loop due to current flowing in the second. Let's do it the other way around. In the second loop, doing it like that. And that is the flux that's going through number 2 due to current flowing in number 1 divided by the current in number 1. So it's exactly the same, except it's not flowing through itself, it's flowing through another one. So here it's flowing through 1, but the current is in 1 and the flux is in number 2, stuff like that. And this is you can call it this if you want, or you can say, well, actually, it might be easier if I consider the current flowing on the second loop and calculate what the flux is in the first one. So then you would, I suppose, talk about L12. In other words, that would be equal to flux 2,1 divided by I2. And the question is this equal to that? And it is. Reciprocity, if you are in material where the B field loves to flux this way as easy as it fluxes that way. In other words, the mu looking this way is the same as the mu looking that way, which is mostly what we're going to have. There are other kinds of materials that aren't like that, but non-isotropic, I guess. But we're going to assume that these are the same. And so you could say, oh, that number is going to be equal to this number. Why even call them some? Why do that? And that's what we call M, the mutual inductance, right? So this is the fancy way of writing it, and this is the cheap and dirty way of writing the mutual inductance. The amount of flux flowing in the other one due to current flowing in the first one, or vice versa. The amount of flux flowing through here due to a current put on that one. And now, that isn't academic. Let's say, and this is problem number 20, I think. Let's say I had, the circuit number 1 is one of these Biot-Savart, big, long, going off to infinity, minus infinity, and then closing it. I'll just write it like this. This is the circuit C1 with a current, let's say, flowing on it. That's like that one there. And then the second circuit is, let's say, just a loop here. This is C2 surrounding S2. So I want to find out how much flux is flowing through this bubble surface. Here I wouldn't make it domed or anything, I'd make it flat. How much B field is fluxing through here due to current here? And so this is I1. I don't even have to talk about I2. I'm not talking about I2 and 2. I'm talking about the amount of flux due to this guy fluxing through there. And you know how that is. The B field is getting weaker and weaker according to 1 over the distance away, 1 over rho. So you would integrate in this direction. And of course, it's independent of, because it's infinite here, it's independent of this distance. So it's just you multiply by the length in the z direction. And then you'd integrate this 1 over rho, and you get probably a logarithm or something like that. And you get the amount of flux that's flowing in number 2 due to a current flowing in number 1. And then you take the ratio, and by George, you get the mutual induction. Right? Easy to do. And the reason it's easy to do is because, by George, the B field of this sort of a circuit, C1, is just equal to that current, I1, all over 2 pi mu, whatever it is, inverse rho, and then it's in the phi direction, or if that's the way you want to write it, like that, and that is the B. Okay, easy to write, and then that's an easy thing to integrate. B dot ds, and the ds could be either taken this way or that way, but it's for sure it's going to be in this dy direction and dz direction. You know, it's going to be an easy integral to do. Think about the other way around. Oh, well, I can get it the other way too. What I can say is, oh, there's a current I2 flowing on here, and I got to figure out how much of the B field is fluxing through the first circuit. Well, the first circuit is all of this area. It's the semi-infinite, everything here. Okay? First of all, that's the integral you got to do, infinite and infinite, right? But worse than that, what is the B field here due to, let's say, this current plus that current plus that current plus that current? It's a pain in the pin feathers. I mean, you can do it. I give you in your little library, you can figure out what the B field is here from, let's say, that arm there, or that one there, or that one there, or that one. You can do it and then add them all up, and you get the B field here due to that. But don't forget, that's going to be a function of where you are, and then you have to integrate that function all the way from 0 to minus infinity, and from minus infinity to plus infinity. And what do you get? The same damn answer. And then you divide by I2, and what do you get? The same answer as you got the easy way. So this is an important formula, and this might be easy, and that's hard. So do it the easy way, okay? Because they're going to be the same. And the thing that proves that, essentially, we call it reciprocity. It's reciprocal. This stuff likes B field to flow this way as easily as this way, right? And then you have this reciprocity business. So use your head. Now, in the example that I handed out, I think last time, you know, a mutual example, what I did is I said, oh, no, we don't have that left circuit is not a single wire, and then you close it at infinity. So what it is a twin lead. In other words, I have a current flowing up, and it goes around and it comes down. All right, now this might be, I think of this as being a long, skinny loop, right? Instead of being just a loop, it's a long, skinny loop, and then I put this here. And now what is the mutual induction between here and here? Well, that's just that same problem one at a time. This one, and then and that one. How much flux? And obviously the flux is going to be going in due to this guy, and it's going to be coming out. They're going to cancel one another almost, but not quite, because this guy is closer than that guy. You understand? You're using all your common sense here. And then you find out how much flux is flowing to this guy and divide by this current. Now I'm assuming that this current is the same as this current, of course, like on a balanced twin lead. So this is more practical. I mean, this is twin lead, and then you've got yourself a little loop over here. You want to find out how much voltage is being induced in that loop, which means induction by M. So you get the mutual induction between this and that. And if you can do it that way, then you can do, and that's what I do in the example that I gave you last lecture, just the little, here I have one twin lead, and I have another twin lead. So if you can do this one, then don't make that just truncated, make that long and skinny also. So you have two twin leads. This is getting more and more practical. Now you have two twin leads next to one another. This one is your voice, and that's your friend's voice there talking to one another. You don't want a cross couple. You don't want mutual induction, because then you get crosstalk. And who causes that? M causes that. So here it's a matter of this is the one induced in here. This how much M. And now, because these are infinite, you don't really talk about henries. You talk about henries per meter, right? Henries per meter, because this is infinitely long and that's infinitely long. That is the example that I gave you last time. I think the thing I handed out today is saying, well, no, that's not the way I have them. I don't have them like this in the same plane. I have them like this. This is how the two are oriented. And that's what this is. That one is an example, and that one, read that if you want to. That's an example of where it's nice to distort the surface. Don't make them both flat surfaces. Don't make them flat surfaces, but you kind of make them distort the surfaces with the assurance that you don't have to have, just so they keep touching the wires. You can have any kind of a surface that you want, as I pointed out for these here, to make the mathematics, the B dot ds, easy. And so that's an example of, again, a useful thing in the sense of you don't want mutual coupling between two twin leads. And also the idea you can distort the surfaces in order to make the mathematics easy for yourself. And then I have another example. I think I left that in my office. I worked it out. A very interesting one. The self-inductance of a coax cable. Now, that's an interesting one. And I will hand it. I should have brought it in today, but I forgot, I guess. Current flowing, let's say, toward you here, and then returning on the surface. All uniform, you know, so it's coming up here, going through some kind of load, and then going back there. Now, think of this. I mean, so I'll draw it in 3 dimensions. So here's current coming out toward you on the center conductor, then it goes through some kind of a load, and here it comes back on the outer conductor. The thing is, this outer conductor one isn't just a wire going back, but it's a wire that envelops the other one, a coax cable. Do you understand what I'm saying? So it's coming up, goes through, and then it's going back. But it is like a loop. I mean, you're talking about a loop here. So even though the current is all coming all the way around, you can consider, let's say, some current flowing towards you here and back here, and there's a long, skinny loop, infinitely long. And then what you're trying to figure out is how much of that loop current is causing flux to go through. And then that B field and H field is circulating around like so, and then you calculate how much B field is passing through, I guess you'd call it, in 3 dimensions, a septum or something like that, a little surface that goes from one to the other, and then maybe a unit 1 meter long. And you ask how much flux is flowing through that guy divided by the current, and you get the inductance of this guy. And then you don't get the inductance because he's infinite, you get the inductance per unit length. And we used to call that L prime, I think, in circuits, part of first part of 311, huh? And that was equal to the inductance per unit length, if I recall. I haven't handed that out, but read that one too, because that's an interesting one. Now the nice thing about the coax, unlike this is called an open line. In other words, there's electromagnetics out in the universe due to the currents flowing here. So there is mutual coupling, especially if they're quite close together. This one here, you could put another coax right next to it like that, and this one is closed. These currents don't cause any magnetic field outside, so there's no mutual induction between these two. All right? So that's why coax is nice, because it's a closed one. It's in its own little world here, and it's in its own little world here. And now, that isn't exactly true. If you have solid, really solid copper, it's true. If you have the kind that you're used to, if you take the rubber sheeting off it, you'll find it's sort of a mesh. It's a woven metal thing. So in some sense, it isn't like real solid copper. It has little holes in it, of course, like a mesh would. And then there would be some cross-coupling, and there's a lot of studies on, well, how much is there and all that sort of stuff. But the ideal would be to have no cross-coupling. Okay? That's that there. You can read about this actually in the book. You can read about it in my notes. You can read about it in this extra set of notes that I'm going to hand out on Monday. But we will have an L prime, and we already had a C prime, and then we found all kind of things out about this, knowing these two things, assuming lossless line, you know, like the square root of L prime over C prime, the square root 1 over the square root of L prime C prime being the speed, and all the intrinsic impedance or characteristic impedance and all that sort of stuff. So these are very important numbers to have, the L prime and the C prime, for understanding that cable, how fast the wave goes and what its characteristic impedance is as the wave goes through the coax cable and stuff like that. Right? All right. I don't have a lot of time. And this is, I should get to this because this is problem 21, but I think 21 is pretty much solved in the notes, in your notes. I'll give you the pages and everything to read. But this is energy stored in L. And like I told you, the purpose of an inductor is to store energy. The purpose of a capacitor is to store energy. One electric, one magnetic. This one is the magnetic, in other words, involving current. So let's talk a little bit about that. Here is this loop. Let's say I have a current in it. I'm going to use a little I, because what I want to do actually is I want to start that little current out at, let's say, 0 amperes and slowly increase it. How do I do that? Well, I have some sort of a, I'll write it like this, some sort of a EMF, a battery or something, that you're somehow making it, now it's 0 volts, now it's 1 volt, now it's 2 volts, now it's 3 volts. It's driving more and more current in there. And this is a function of time. Okay? And of course, what that's going to do is that current is going to cause, need I talk about it? It's going to cause a B field and an H field here. And then you integrate over this surface. This is the C, this is the S sub C. You integrate over that surface, that B dot ds, and you get the amount of flux that's flowing, and it's a function of time. It's increasing little by little by little. Now, I don't know exactly how to say it. Let's say I take a bowling ball. This is a mechanical analog. Let's say I take a bowling ball, sitting still, that's comparable to no current. Nothing's happening, it's just sitting still. And then what I do is I try to accelerate this guy. Get it from 0 velocity to 1 mile an hour or something like that. What do you find? Do you find it's easy to do? Do you find that actually the bowling ball is pulling on you? What do you find? No, what you find is there's a force of reaction trying to prevent you from accelerating that ball, right? I mean, then the heavier the ball, the bigger the mass is, the harder it is to get it going, right? That's exactly what happens here. What happens is you are trying with this voltage to increase this current, and then Mother Nature will induce another voltage. This is Faraday's law of magnetic induction that I'm talking about, which we will understand much more fully in the second half of the course. But what it does is it produces a voltage, V induced. This is the EMF this is just the battery that you're increasing to get this thing going. And this one, if you notice, he's directed opposite to this. That's just like the force of acceleration, according to Newton, is in the opposite direction to the way you want it to go. Okay? And then how much is that? How much is that? It's equal to the rate of change of that flux with respect to time. So if you're trying, and the same thing with a ball, if you try to take that ball of a certain mass and accelerate it really fast, what? You find the force is a hell of a lot more, right? The force of reaction of Newton. Well, same thing here. If you try to increase this current really fast, then you're going to find that the voltage is going to be bucking you. It's going to be larger, bucking you, trying to negate what you've just been trying to do. Now, you will beat it out. This will keep increasing, but it won't be like this is 0. I mean, it'll be some sort of voltage. So this might be 10 volts, and this might be 9 volts. So really, it's only 1 volt. Causing 10 amperes, and this is causing 1 ampere. 9 amperes, you'll only be really increasing by 1 ampere. That's what's happening. And so this is the voltage induced in there. Now, it's you don't see it there. I mean, there isn't any battery, nothing there. I mean, you don't physically see it, but it's there. Okay? Now, I've pictured it here, but it's actually all around this baby. In other words, you could picture it as little guys, little guys, little guys, little guys, all the way around, all oriented that way. And if you sum them up, it's that. So it's the circuit way of presenting a voltage, just like this is presenting a lumped voltage right there. And then now, I don't know how you study this in circuits, but when you talk about energy delivered from a voltage source, the current is coming, like for example, here's a battery, plus to minus, and then you talk about, and then here's a bulb or something. Here's the current. The current coming out of the positive terminal. You take the voltage here and times the current that is being caused, coming out of the positive terminal, and that is the amount of energy being supplied by this fellow here, all right? Now, if you want to charge this guy, if you want to charge that battery, what do? You plug it into something such that the current is forced down the throat, like so, the current flowing into the positive terminal. That's charging that's what you do when you charge your automobile battery. You are connecting the positive terminal to the positive terminal of some source that's forcing charge into the gullet, so to speak, of that battery. Well, that's what's happening here. What you're doing is essentially the current is flowing into the positive terminal of this induced voltage. All right? That means that you are essentially, how would you say it? You're doing work. Like when you're charging up a battery, you're doing work on that battery. You're doing work on this circuit. Okay? And unfortunately, the time is up. This is problem 21. I would say do 20. Don't do 21 because I'm not finished with this yet. I have a ways to go, in fact. Okay. All right. See you on Monday.